Hello everyone, and welcome to the very first session of our 3D Thursdays webinar series. Myself Leela Krishnan, working as an assistant manager at Wipro 3D. I'm thrilled to have you join us today as we explore the exciting world of additive manufacturing and its transformative impact on space technology. As many of you know, additive manufacturing or 3D printing is revolutionizing various industries, and today we will be focusing on how it's redefining space exploration and technology. Our title for this inaugural session is Redefining Space Technology with Advanced Additive Manufacturing Applications. We have an engaging agenda lined up for you today, which includes proficient geometries at first, which discovers how additive manufacturing enables complex designs for spacecrafts. Secondly, we will see material innovation, where we can explore advancements in materials essential for space applications. At the third point, we will see reduced part count. Here we learn how 3D printing simplifies assemblies and enhances reliability. And finally, we will see in-space manufacturing, where we will be discussing the potential of manufacturing directly in space. We encourage an interactive session, so please feel free to ask questions. We will have a dedicated Q&A segment towards the end of the presentation. Until that, we will be open to take your questions through the chat feature. To ensure everyone gets a chance to participate, we may group similar questions together. We will address as many questions as time allows, so don't hesitate to share your thoughts. Lastly, please note that this webinar is being recorded. By participating, consent to the recording being shared for educational purposes. Now, it's my pleasure to introduce our General Manager, Mr. Ethiraj Kasal sir. Ethiraj sir heads Wipro Infrastructure Engineering's additive manufacturing business and provides overall business and technical leadership for Wipro 3D. With over 25 years of experience in the aerospace and automotive domains, he brings deep technical expertise across the entire AM value chain from conceptualization to certification. Ethiraj sir has been a key contributor to the evolution of additive manufacturing in India and the Asia Pacific region. He holds 6 patents and 3 trade secrets to his credit. Prior to his role at Wipro 3D, Ethiraj sir has worked with prominent companies like GE, Honeywell, Infosys, and Turbotech. Please allow me in welcoming Mr. Ethiraj Kasal sir for the formal launch of our webinar.
Thank you, Krishnan. Good afternoon, everyone. I'm really thrilled to welcome you all to the launch of our new monthly webinar series, 3D Thursdays. So as the General Manager and Business Head of Wipro 3D, it is my pleasure to kick off this exciting initiative that will bring together industry experts, enthusiasts, and innovators in the field of AM or 3D printing, in other words. So 3D Thursdays will be held on the third Thursday of every month at 3 p.m. You can all mark your calendars so that you don't miss the future sessions, third Thursday of every month at 3 p.m. This will provide a platform for us to share knowledge, discuss the latest trends, and explore the endless possibilities that the 3D printing or additive manufacturing offers. So our goal with this platform is to basically create a community where we can learn from each other, inspire new ideas, and drive the industry forward by sharing what we have learned in our additive journey. So today marks the beginning of this journey where we will be delving into the various aspects of 3D printing from cutting edge technologies to practical applications across different sectors. So the first one today is going to be on the space technology. The title is Redefining Space Technology with Advanced AM Applications. You will learn many applications. You will see many applications once Akshatha starts the session. So we have an exciting line of speakers and topics that will not just educate, but also really spark very meaningful conversations and collaborations. I definitely encourage all of you to actively participate, ask questions, and share your insights either during the session or after the session. And together, we can definitely push the boundaries of what is possible. And with 3D printing making a significant impact on the future of manufacturing. So once again, thank you all for joining us today. And I really look forward to seeing you at our future webinars as well. So let's make 3D Thursdays a resounding success. Thank you. Over to you, Krishnan.
Thank you, sir. Now I'm excited to introduce our speaker for today's session, Akshatha Hulmani Dayananda. Akshatha ma'am leads the advice offering of Wipro 3D and is in her second stint with the organization, focusing on training and consulting opportunities for the group. With a dedicated 11 years of experience in additive manufacturing, out of a total of 16 years in the industry, she has worked across various verticals, including research, AM, OEMs, and services. Her extensive background equips her with a comprehensive understanding of not only additive processes, but also the challenges users face in adopting AM. Akshata ma'am's passion for additive manufacturing drives her commitment to spreading knowledge and accelerating its adoption. Let me welcome Akshata ma'am as she takes us through the today's presentation.
Thank you so much, Krishna. We hope that the audio and the video is working fine for everybody. Since Leela has already introduced me as well as the topic for the day, I would like to briefly introduce Wipro 3D because it's important for you all to know the company and the capabilities that we represent today. Wipro 3D has three major offerings. That the first one is print services. Wipro 3D provides print services with both metal as well as polymer. This has been a long-lasting offering of ours from a long time. Uh, Based on all the experience that we have gathered because of the print services, we also offer AM training and consulting. So all the knowledge learnings that we have, we like to share it, and this we do it in the way of training and consulting. Other than this, we also help AM enthusiasts set up their own AM center, which we call as turnkey solutions. So we engage with the interested customer, understand what their specific need is, and then tailor make a facility like an AM COE center or a production center, and we deploy it for them. We can also operate the center for a few years and then hand over the center completely to customers with printers, accessories, softwares, everything. And it must be noted that Wipro 3D also makes polymer printers, and that is what is the products offering that we have. We have a polymer printer which works on the principle of FFF technology. It's called F300-2. So when we print with metal, we print with various alloy families. It could be steel, aluminum, titanium, nickel, and even some custom alloys, which is not readily available for printing. We can develop the parameters and do the printing in those. When it comes to polymer, you see the list on the screen, and this is just a representative list, and we can do much more. Wipro 3D is the only NADCAP certified AM facility in India. We also have other certifications like ISO 9100, ISO 9001, etc. These certifications show how robust our processes are, that we understand what are the key variables in the processes, and also that how well we control all these key process variables. We are also the company which have put out a lot of certified AM metal parts, and the totaling number is 10. Here we have about 8 pictures, but I think in India we have the most number of certified parts which are deployed both in the aviation or the aerospace sector. So coming to today's topic, the first and the foremost thing that we would be going through are the case studies. So what we've done is we have categorized these case studies into proficient geometries, material innovation, reduced part counts, and in-space manufacturing. So we will discuss case studies in these categories. We will also then be able to understand what are the current trends and innovations happening in these four fields. And you will also get a glimpse of what is coming in the future. One very interesting thing that everybody should note here is that these are also the value additions that AM brings to the table. So proficient geometries or efficient geometries, or let's even say complex geometries, is a value add that additive can bring to the table. Material innovation. There might be materials um, that we can print now and maybe not before, or maybe we can print two materials together, right? So this is another value add that is put on the table by additive. Reduced part counts. It's also called as monolithization. It's also called as part consolidation. So we have all this grouped under reduced part counts, which is also a value add from additive. And last but not the least, in-space manufacturing. I think this will be the coolest part of the webinar. I'm looking forward to present all of these to you. So let's get started with proficient geometries. Here is an example by SpaceX, and this is a Draco engine, and this is amongst the first rocket engines to be 3D printed entirely. Why I say that is because now there are a lot many more engines that are being printed. And to just highlight, if you look at the region which I am highlighting now, you will see AM achievable geometry put up there. So it is possible to achieve extremely complex geometries using additive. And the value add over here that SpaceX saw was that they had a very flexible production process. So any small improvements, changes that they want to make, it's very easy to start implementing these changes. Uh, Very often people think that additive is extremely expensive, but in this particular case, the component was delivered at a reduced cost and also reduced weight condition. So this is quite a critical part, which was the rocket engine. But here is another example, and this time it's from Japan. And it's a very unique kind of example over here. If you look at the lattice kind of structured part here, these have been used as shock absorbers. So they're all fitted at the places where the green mark goes, and they basically act as shock absorbers when it lands on the lunar surface, right? And it is designed to crush on landing so as to give a softer impact. So very unique solution that they have used additively manufactured part for. Again, it is a complex geometry, but works very efficiently. So we at Wipro 3D have also been making some very complex structures. For example, MINS cluster is one of it. And you can see how complex the geometry is. This is made from ALSI 10mg. It is one of the alloys of aluminium that we can print with. And many different parts were also integrated with this one. So it's complex. It also has part integration. It also performs better. So it's our observation that not any one application usually has more than one value that is delivered. And that is what is mentioned here. So this is a stationary part that we have. And in the next example, here we have a rotating part. So this is an impeller also made with ALSI 10mg. And you would definitely understand that these moving parts or rotating parts are a bit more difficult to qualify or get certified with. But this is the trend or the state of the art thing that I wanted to show, that we have slowly gained confidence with the stationary parts, and now we're moving to rotational parts and more critical parts. So this is the trend that I would like to point out to with these case studies as we progress. Also, what we have here is very interesting. So we all know about Vyomamitra. So she is the robot who is going to be put on space with a lot of sensors to understand what a human being may experience when they are in space, and to also check, how the different maneuverability and all that works, right? So she's called Vyomamitra, and we have printed the torso of this particular robot, both the front and the back, and I'm sure that many other parts may also be 3D printed. So this was in the news and a very unique application. Now, the advantage that you get when you do this with additive is that you get the parts faster and you don't need too many numbers of it, correct? So you may need a couple of them. So these kind of cases, so quite large parts, but also where the design is very unique, you do not want to spend a lot on maybe tooling or machining, programming, setup, and things like that. Additive becomes a great tool over here. So this is another interesting example from ISRO, and it was Wipro 3D's milestone when it comes to India and the space program, that we printed the first metal part which went into space. So this is called the, it's an antenna part. It's called the feed cluster, and it went up on a satellite GSAT-90. This went through a lot of rigorous testing and has been in orbit since 2017. So waveguides like this are also a very ideal application. So with this section, we have seen some of the complex geometries that are possible to achieve with additive manufacturing. But again, I would like to iterate that for any one case, it's not that we will have only one value addition which AM brings. There could be more than one. Let's move on to see what's happening in the world of material innovation when it comes to AM and space applications. Here is an example where a multi-material, basically two different materials are used here when I say multi-material. A multi-material nozzle has been 3D printed, and a lot of testing has been done on this particular injection nozzle. So this has been achieved by Quadrus Corporation's Advanced Manufacturing Division. When you have two materials, what is happening over here is that the thermal management has become better, as in the part is able to manage the thermal loads better, and the design can be very complex as well. So the company has overcome numerous hurdles which are associated with the bimetallic process. So the most proven process for additive manufacturing is LPBF, which is laser powder bed fusion. And printing with two metals in this particular technology can be quite challenging, and there are a few hurdles. So now I'm also bringing about some challenges that the industry sees or the technology sees, right? So all these hurdles have been overcome by the company, which, let's say, includes the risk of material cost cross-contamination and maybe the formation of high-strength metallic bonding. So there were a few challenges and hurdles, but they have been overcome, and bimetallic printing has happened. So this is one material innovation. Another one is printing with magnesium. So this is again from Japan. It has a group of companies which have worked on this. So it is known that magnesium is much lighter than, let's say, even conventional aluminium, but it could deliver the same kind of function. So here they have developed the process or refined the process, let me say, to print with magnesium. At Wipro 3D here, we have also done similar projects where we have adopted a very new material to be processed through the LPBF technology. One such example is the heat resistant steel. Now, the part over here is called as the inner ring, and the material that is used to print this is heat resistant steel, for which there were no existing parameters. So Wipro 3D made the specifications for the powder, bought the powder, developed the parameter sets, and also reverse engineered the geometry, and then delivered the entire solution to HAL, which was certified by Semilac. So here, this is a aviation kind of an example, but we have done something very similar for the space sector also, wherein this LPFT straightener or straightening device has been printed with a material called as 08X commonly, and this is also one such innovation. So there are probably newer materials, or like we saw in the first case, a combination of materials that can be printed with additive, which will give us parts that perform exceptionally well. So this is another trend that I would like to bring to your notice. Now, the third set of case studies are going to be on reduced part counts. And like I mentioned before, some people address this as part consolidation, some people address it as monolithization. So basically, it is about systems design. You combine the design so that the part count reduces, but then you're looking at how the entire system works rather than how the component works. So here is an example from a company called as Northrop Grumman. All right. Now, what's special about this is that there is consolidation of parts over here, which improves the performance, reduce the cost, reduce the lead time. But what's special, like I was saying here, was that it's possible that this is done even in the electron beam powder bed fusion technology, or even with another kind of metal printing technology, which is called as DED. So these kind of complex parts or even huge parts, all of them can be done together, not only in the laser powder bed fusion technology that I mentioned before, but DED and electron beam technology as well. Very recently in the news was this particular engine, which is Raptor 3. So that's the image that you see on the far right. And the image that you see on the far left is the Raptor 1. And you can just see how many different parts have been combined to make the design much more elegant and efficient, right? So all the flow paths for which all this wiring was needed have been integrated into the design. I have a picture of the cross section as well. So I will show that. This is a much lighter part and a much more efficient part. I think this is where we start moving from almost science to art in a certain way. And here's the cross section of the same part. This is by SpaceX, this engine. And let me go back and let you have a look at the cross section and how complex it is. It's not that this was done in one part. Again, this was done in a few sections and joined together. So this is not one full build, but nonetheless much lesser than before. So they have reported that they have 21% more thrust, right, while being 7% lighter. So this is the advantage of reducing the counterparts. And here's where we would like to show you the second milestone, or another milestone that we have reached along with ISRO. Thanks and hats off to ISRO for designing the PS4 engine, the PS4 combustion chamber, which in a way that it could be 3D printed. So the geometry you're seeing over here. And this is to power the fourth stage of the PSLV. PSLV is ISRO's workhorse launch vehicle for Earth observation and scientific satellites. Here, consolidation of multiple intricate components was done into a single unit, thereby boosting the production efficiency and also the structural integrity. And ISRO thinks and comments that this is a step forward when it comes to sustainable space exploration. The hot test of this particular component was done on the 9th of May 2024. It was all over the news. You can also look it up. And it was to deliver a thrust of 7.33 kilonewton in vacuum condition. So this is a very great milestone for us, and it is our joy to share it with all of you. Then we have also had a lot of waveguides with very complex channels like this that you see on the screen being made. The first one you have already seen. This is the feed cluster, and there are many more that we have worked on. Now moving on to the last section, or the value add, wherein I will share some more case studies, is the in-space manufacturing. I'm quite excited to share these examples, and I hope you will be equally excited when you hear about this. So this is an exercise by NASA, wherein they sent a polymer printer to space, and they also printed in space. So what they printed was a simple tool like this, but also you could say a calibration part, like what you see over here. And it was brought back to Earth, and measurements were made and all of this. So that's really very cool. And if you were thinking that it was only polymer, the European Space Agency, ESA, along with Airbus, sent a metal printer to space as well. And they have also printed these coupons in space. This was done with SS316, and the form of the raw material was a filament. So here also there were quite some adjustments, or let's say adaptations, that were made, as in the metal printer had to be as compact as, let's say, a washing machine. And printing in vacuum comes with its own challenges. This printer is able to print a volume of, let's say, 9 centimeters high and 5 centimeters wide. So that's how much it can print. So this exercise is also being done by ESA. But I think the most interesting one would be this. So does this look similar? I hope so, right? It looks like a Lego block, and it is done between Lego and ESA. So what they are trying to do is they're trying to evaluate if using whatever, if you can call it soil, let's say lunar soil or Mars soil, you can make blocks like this, like the Lego blocks, and then stack them on one another to have a construction of some sort, like a shelter or something like that out of the space. This has not been printed in space or on Moon or on Mars. What they have done is they have located a meteorite, which is 4.5 billion years old, which they found in North Africa about 20 years ago. So they collected that meteorite material and they have mixed it with PLA, and then they have printed this on Earth, and they are calibrating or checking if the same can be done with, let's say, the lunar soil, right? So this was also something very cool. Now, already I have shared some of the challenges, right? Like for, let's say, when you're trying to print with two different materials, what are some of the challenges? When you try to print in vacuum or in space, you already know what are the challenges. So I've mentioned a few challenges, but there are some other generic challenges that I will also point out to. But instead of thinking of them as challenges, I would really like to represent them as possibilities. For example, let's say if I look at the design and engineering part, today the challenge is that there are a lack of design engineers who are well aware of the AM process. But it also means that it's a possibility, right? That more the people get trained on this, we will have much more complex or efficient designs. Also in manufacturing, uh, there's a certain limitation of size. We can't do very huge parts, or maybe when it comes to material, we can't do a lot of materials, maybe not as many as in casting process, or maybe the production cost is high. So it's always a possibility to come up with new processes or technology which can resolve this problem and print really large parts or print different materials and at a lesser cost. Now, we're talking all about AM printing and all of that, right? But what we usually neglect is post processing also. We need to also develop the post processing techniques. When I mean post processing techniques, what I mean is, let's say, when you have a complex flow path internally, how are you going to remove the powder? How are you going to even inspect if all of the powder is removed? So these kind of post processing techniques also have to be evolved and developed. When it comes to the service, there are a few standards which are available today. There are not as many as for other conventional processes. That's a challenge, but it also means that a lot of research can be done by the educational institutions or by research centers to develop and contribute in developing these standards. Which brings me to the almost last kind of a section, and that is the regulatory advancement. So we did an exercise in the beginning of this year wherein we tried to see how many standards are available for AM. So ASTM, which is the American Society for Testing and Materials, they have set up this F42 committee or organization, which is like the oldest committee which have been developing standards for AM. And they have 8 subcommittees. So if you look at the year-wise data, you'll see that the number of standards that they are putting up every year is going up. So there are quite a few standards which are available today as compared to, let's say, 5 years back. And you see this big spike in 2023. We are still, when we did the exercise, we were in early 2024. So probably they would put out an equally good number of standards by the end of even this year. Now, if I try and see in what category were most of the standards developed, and the categories being design, manufacturing, materials, quality, etc., then the highest number of standards have been published for materials, right? It's close to 30 standards. And there are definitely standards for design, for manufacturing, and also for quality. They have put out standards which are material specific and also which are industry specific. So for example, TI64 is an alloy type which the medical industry uses a lot for implants. So they could have a TIE 64 related material standard specific to the material industry, or let's say inconel 625 material standard, which is very specific to the aerospace industry. So they are doing a lot of these standardization, and it could be general, but it could also be very, very specific, like I just pointed out. So there is a lot of progress which is happening here, which will eventually help us to put more and more certified and qualified parts into the space. Now, in materials, if we look at what was the division of the uh, standards between metals and polymers, you'll see that 50% of the that was put out was for metals, and polymer is also quite close. Here is NASA's Perseverance rover, and this has 11 metal parts that was taken to Mars. All of these are certified AM parts. Now, like mentioned over here, 5 of the 11 metal AM parts are for an X-ray lithochemistry. They call it the PIXL, and 6 are on an instrument called as the Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE. So it is for all these instruments which will require a lot of refined and complex components that they have done this. And how NASA is able to do this is because they have put in a lot of guidelines, they have put in a lot of standards themselves. Of course, these are all internal standards, and they have this methodology of certifying or qualifying the parts. And once they've gained that confidence, they are able to these many parts in space. So over here, I hope that we have stressed what is the importance or the values that have been contributed by additive manufacturing to the space industry. We also discussed a lot of case studies and examples while understanding what is happening now, but also what are the future prospects and challenges to overcome. We've also seen some regulatory and safety considerations.